A broken egg never unbreaks, yet physics runs both ways. So why does time pick a side in our universe? The immediate takeaway is simple. Disorder wins because the cosmos began in a strangely ordered state. You do not need equations for that, you only need a feel for huge numbers. Think coffee swirling into cream, never the reverse. Think smoke drifting apart, never regathering neatly. Now scale that up to galaxies, stars, and black holes. The same bias shows up everywhere we look. We call it the arrow of time, pointing from past to future. It is the direction where entropy rises. That word just means more ways to be messy than neat. Today we will see how that bias forms, and why your memories line up with it perfectly. Start with a kitchen scene, quiet and bright. An ice cube melts on a warm plate and water spreads. The arrow of time means change has a preferred direction. Melting happens and unmelting does not. This matters because every life process depends on that tilt. Batteries discharge, bodies age, and engines waste heat. Under the hood sits a counting game with absurd stakes. Entropy counts how many micro-arrangements match one big picture. There are vastly more jumbled arrangements than tidy ones, so random pushes drift toward jumbled again and again. Here is how the drift works in plain words. Molecules bounce in chaotic ways, while totals like temperature stay steady. We group many details into one label, like warm water. That grouping hides countless possibilities we never track. Most possibilities look mixed, not separated. Example in real terms. A perfume bottle opens and the scent fills a room. Between 10 to the 23 and 10 to the 24 molecules explore space. The divided state has far fewer ways to arrange them. The mixed state has astronomically more. You will never see a room refocus the scent. Air jostling would need a miracle alignment, beyond unlikely. Bottom line, the common state wins by sheer numbers. Shift to a tabletop with glints of light, calm and focused. We do not watch every molecule because that is impossible. Coarse graining means we bundle tiny details into big summaries. That bundling defines what we call order or disorder. It matters because the laws themselves do not force forgetting. They run forward or backward just the same. Our summaries do the forgetting by design. Here is the working picture in slow steps. Microscopic motions preserve volumes in their abstract space, but when we blur positions into boxes, we merge distinctions. Blurring folds many precise stories into one looser story. That looser story almost always looks more scrambled. Tiny test. Could a camera recover positions of all air molecules, not without recording a ridiculous amount of information? Erasing such a record has a heat cost every time. Clearing 1 bit dumps kT log 2 of energy as heat. At room temperature, about 3 times 10 to the minus 21 joules. Labs have confirmed that cost in controlled devices. Example in plain tech terms. A drive that wipes data will always warm a little. The warmth is the price of forgetting microscopic truth. Forgetting tilts the tally toward states we call messy. So the picture is, coarse stories flow toward higher entropy. Pull back to a baby cosmos, soft glow across darkness. The early universe looked smooth, hot, and astonishingly uniform. Arrow of time, meet your root cause. Low gravitational entropy made that smoothness rare and special. This matters because gravity flips our everyday intuition. For gas in a box, clumps look ordered and fragile. For gravity on cosmic scales, clumps unleash options and motion. More clumping means more ways to arrange gravity's fields and matter. Here is the engine at work. A uniform haze has few possible gravitational configurations. Start tiny ripples, and matter can fall, heat, and radiate. Collapsing patches light up stars, fuse elements, and spew energy. Black holes form and store staggering amounts of entropy. One sentence recap. Smooth was special, lumpy is typical, so time flows toward lumpy. Now an example with numbers you can picture. The cosmic microwave background is smooth to 1 part in 100,000. That smoothness means an extremely low gravitational entropy. A solar mass black hole holds about 10 to the 77 units. The monster in our galaxy holds near 10 to the 90 units. Across the universe, black holes likely some near 10 to the 104 units. Net result, the future has room for staggering entropy growth. Zoom into a chalk dust cloud under bright lab lights. Microscopic rules mostly run fine backward or forward. Newton's equations and Schrödinger's equation both respect reversals. A movie of ideal collisions can look right in reverse. That raises a famous challenge about direction. If laws are symmetric, where does the tilt come from? The answer again points to conditions, not rules. Typical states rush toward higher entropy under either direction. Only a contrived state runs downhill the other way, now a twist at the particle frontier. Certain decays violate time reversal at tiny levels. Neutral kaons and B-mesons show direct time asymmetry. The amounts are small, near parts per thousand or less. They were nailed by experiments across decades of work. This is a fascinating fact, but not our driver. Your coffee does not care about weak force phases. Friction, mixing, and heat exchange set the visible tilt. Example you can replay in your head. Billiards scatter on a table and then seem to unscatter. That backward clip needs the starting positions tuned perfectly. A breath of air ruins the trick instantly. Real rooms never deliver that cosmic luck. So the anchor idea is symmetry holds locally while conditions set direction. Cut to a colorful debris field, shards glittering in space. Irreversibility looks like damage that spreads and never recoils. The core idea is simple again. Energy flows from concentrated packets to diluted baths. We care because this governs engines, climates, and even metabolism. You cannot cache the same heat twice for full work. Here is how the flow enforces direction. Hot to cold boosts the count of available arrangements. Friction turns organized motion into jostling, which looks like heat. Turbulence shreds patterns into eddies, adding more mixed states. Chemical reactions find easy downhill paths, dumping heat outward. Rule of thumb. Any process that creates heat leaves footprints that are hard to erase. Real numbers help fix the feel. A fridge moved into a warm room draws hundreds of watts. Its back coils throw more heat than the box can remove. The room warms overall, while the inside cools locally. No loophole appears when you count the entire system. Supernovae tell the same story in grand style. Nuclear fuel concentrates energy in a star's core. The explosion spreads that energy through expanding gas and dust. Shock waves heat clouds that then radiate into space. What to remember, energy dispersal writes one-way tracks. Glide through a web of galaxies, faint threads under blue light. Several arrows actually point the same way in practice. Thermodynamic, psychological, computational, and radiative all align. The arrow we feel is the one our brains use. In one breath, the psychological arrow is memory forming only toward the future. It matters because decisions need records that stick and persist. Brains are warm, wet, and constantly dumping waste heat. That waste enables writing stable changes into synapses. Computation mirrors this need for trails. You can compute reversibly, but you cannot forget for free. As we saw, erasing records generates heat, which adds entropy. Radiation adds a cue you can literally see. We receive waves emitted in the past, not advanced waves. Absorbers around us suppress advanced solutions by their boundaries. Light leaves stars and scatters while nothing gathers it back. Now a concrete scenario with a number. Cameras write megapixels of data per frame every second. The storage growth costs energy, adding measurable heat loads. Telescopes collect ancient photons, always from earlier times. We never film tomorrow because the light has not arrived. So the picture is records, radiation, and heat walk in lockstep. Dive toward a glowing disk circling a dark sphere, sparks flaring. Could time ever run backwards somewhere, even for a moment? The honest answer is, not for anything large and ordinary. Local dips happen, but giant rewinds are beyond fantastically rare. That matters because people ask about loopholes and demons. Maxwell's famous demon tries to sort gas into ordered sides. When the demon stores and erases information, heat rescues the rule. The accounting closes with that tiny k-t log 2 cost. Here is what might seem tempting. Fluctuations do create little islands of lower entropy. They are small, short, and drown in the larger tide. Big islands would require absurdly exact alignments across many parts. The odds fall like double exponentials with system size. Cosmology raises a different twist with deep implications. What if brains just pop from noise with fake memories? That nightmare loses to the story we actually observe. A shared past explains the same arrow across distant regions. We see consistent fossils, backgrounds, and growth everywhere. Advanced civilizations will still face heat budgets always. Even near black holes, local arrows track available free energy. Accretion disks heat, radiate, and spin down as entropy climbs. Bottom line, backward movies are math toys, not living worlds. Now fade back to the quiet web that opened our tour. Broken eggs, melting ice, and star fields all told one story. The universe began unusually tidy in a gravitational sense. That is why disorder wins and why your memories point forward. I post deep dives like this every week, gently paced. Subscribe if you want more clear, cinematic trips through physics. See you in the next one, out there among the threads.